In this video, I'm going to give an overview of big O notation and algorithm growth rates, which is often associated with data structures and algorithms. I have a companion video to this which goes over the Java collections framework and abstract data types and several examples that follow. But nonetheless, I do want to consider a bit about big O notation. What is big O and why is it important? In short, algorithm efficiency and scalability, and this is a concept that is getting even more and more important as we have connected devices that are oftentimes consumer owned. So think about your mobile device and think about all the things that you can interact with your mobile device. Your pressure cooker, your home alarm system, maybe self-checkout when you go to the store. So the trick is that the number of mobile devices in the world is humongous, and that means that we need to be able to prepare for lumpy demand, and we need to be scalable because of it. So Big O is a funny thing for me because I did not have exposure to Big O when I was an undergrad. I came from an information systems program in College of Business at Miami University, and we simply weren't talking about algorithms. We were talking about using computers to make a competitive advantage. Now, when I became a professor, about 5-6 years into being a professor, the department head at the time asked me to teach the Data Structures and Algorithms course because he wanted to try a new approach to it. And I said, sure, fine, with the only footnote that I had never taken a class in data structures and algorithms, and I knew nothing about it. So I taught myself and then taught the course, got great reviews on the course, I remember, and it became one of my absolute favorite courses. Unfortunately, it's not taught standalone anymore. It's now part of a Computer Programming 2 course, but a real eye-opener for me, and actually, it really helped me to understand math because I could visualize things like what a logarithm is. So, what is Big O? Well, what we're looking at is as in the number of items to process grows, how much more T or time is required to process those items. Ideally, we want to minimize the T that's required for additional N. Now, N could be something like number of items in a collection, for instance. Maybe number of items in a shopping cart or number of customers checking out. So if we do have lumpy demand, as we saw a lot through COVID, through hoarding and then the following kind of lull, as we have this lumpy demand, we want to be able to make sure that our software can handle it no matter what the demand is. When we think about big O, we tend to think O to the 1, O to the n, O log n, log base 2 by the way, O n times log n, O n squared, O n cubed, and we could even go to O n factorial, so on and so forth. But to make it a bit easier, I've created an Excel spreadsheet here with the number of n right here. So n, again, the units that we want to process. And then I have the algorithm that we're applying right here. So O to the 1, O to the n, O n log n, so on and so forth. And the amount of time it would take to process that is what you find in the body here in column F all the way through column AF. So it is kind of funny. O to the n means every additional n is one additional unit of time. So I kind of use that as my baseline. So O to the n is essentially a diagonal line. Every new n we add is one more unit of time to process. So that's our baseline. O to the 1 means that doesn't matter how many items we have, it's essentially a flat line. It's going to take the same amount of time to process it. And that's the ideal case because scalability is built in. We can have infinite n, and the unit of time is going to be the same regardless. So I mapped these out and I put those into the presentation that we're about to jump into so that we can take a look at these and do some compare and contrast. So let's start with O to the 1. This one's the holy grail. This, as I said, no matter how many n we have, it is constant time to process. Examples of O to the 1 is storing an item into a hash map or a hash set, or retrieving an item from a hash map or a hash set. And the reason is, with a hash map or a hash set, we are storing an item not in the order in which it was added, but we're doing a computation based on an inherent state of that object. In other words, we could take an object like a string and create a unique hash code for it, or somewhat unique hash code for it. And then that hash code becomes the address of where that string lives in our collection. So if we want to add that string, we know exactly where to put it. If we want to retrieve that string, we know exactly where to get it, and we can use a simple algorithm to find that address regardless of how big or small the collection is. Also, if we're at the end of an array list and we want to add something to the end, that's O to the 1. We're simply adding something right there. Or if we have a specific index number from an array list and we want to retrieve the item from, say, compartment number 13, we can go directly to compartment 13 and grab that item. So those are examples of O to the 1. Also, any statement that's only run maybe one time or a given number of times in your program, regardless of the data set, that would be O to the 1. That's the Holy Grail. It's very flat. And the goal with all of this big O notation is to come up with the flattest curve we possibly can come up with. So O to the n is another one that's going to make a lot of sense, and this is essentially a 45-degree line. That means for every additional n, it takes exactly one additional unit of time to process. A common place where we'll see this is iterating over a collection. So like a for each loop, where we have a collection and we're shaking hands with everything in that collection. So think about that. The more items in that collection, the more handshakes we have to do. Each handshake would essentially be a unit of time. So this ends up coming up as a 45-degree diagonal line, not surprisingly, with n down here on the bottom and t over here on the side. And you can see the difference between O to the n and O to the 1. Essentially, as we get more n, the additional time to process those n is the difference between this O to the 1, or this flat line, and this diagonal line that's here. Now, it doesn't look exactly diagonal because, you know, this image is skewed a little bit, but that essentially is a diagonal line. Now, O log n is kind of a neat one, because O log n is the first opportunity we really have to take a steep curve and flatten it down. And we can do this with recursion. Oh my gosh, that sounds tricky, but not really. Remember I said O to the n would be shaking hands with everything in a collection. But we don't always have to shake hands with everything in a collection, right? Think about if you look me up in the phone book. So you look up Jones Brandon. Would you start on the first page? Phone book, I know that's a bit of an anachronism, but you trust me, you know. Remember what a phone book is. Would you start with the first page of that phone book and start with the A's and read all the way until you get to the J's? No, you wouldn't, would you? You'd probably take the phone book and open it up about halfway and see if you're beyond the J's or before the J's. Let's say you're beyond the J's. Okay, well then you're going to take that half, the first half, and you're going to cut that in half and see if you're before the J's or beyond the J's. In that case, you might be before. So you take that kind of that middle quarter, and then you cut that in half, and then you repeat, repeat, repeat. And that essentially is the definition of recursion, where you're taking the same algorithm and you keep applying it over and over again to a smaller and smaller data set until you get to your answer. And I'm sure you'd agree with me, it would be a lot faster to find Jones by continuously cutting the phone book in half and half and half until you find Jones than to start at the very first page and read every single name until you find Jones, or good Lord, if my last name were Ziegler or something like that, you'd have to do quite a bit. So you see, that's how we can take a diagonal line, which is O to the n, and flatten it down to an O log n line by applying recursion. Now, what's a logarithm? Oh my gosh, was that back from the math class you took and you totally forgot about? And this is one of those times where I say this is where I really enjoy data structures and algorithms, because I could visualize what an algorithm is. Think about what an exponent is. If you think exponential growth, you think about a line that's increasingly getting steeper. We'll take that line and effectively rotate it 45 degrees, or do the inverse of it. And that gives you a logarithm where you can see we start with very fast growth, but as the data set gets larger, the growth moderates and actually slows down. So we get a curve like this. Now, over here on the right, I have a graph that has O to the 1, and then O to the n, our diagonal line, and then O log n. So look at this. By using recursion, instead of reading every single entry from start to back, we start with a diagonal line and we flatten it to this log n line, which isn't so efficient in the beginning, but gets very efficient as we have a large data set. So we'll see an example of this when we look at heaps and binary search trees and things like that. We'll see how we can use recursion and logarithms to store more and more data effectively. That's essentially a deep dive, about 15-16 minute video I have that just goes into that process, but it helps to visualize with an example over and above my phone book example of how we can use recursion to flatten this curve. Okay, and here's just a zoom up. This is O log n compared to our O to the 1. So you see initially fast growth, but it slows down as we go further and further. You see here we're all to 25. If we were to expand this to 100, 10,000, something like that, you'd see this line would get increasingly flatter. So actually the time to process gets better and better. Not necessarily better, but yeah, it gets increasingly less worse as the collection of data to process increases. I hope that makes a bit of sense. Okay, O(n) squared. So this is truly exponential. And once again, the graph is a bit skewed, but you know what an exponential curve looks like. This is oftentimes what we'll see when we have a loop within a loop over the same collection. And so in other words, we have an outer loop that's shaking hands with each item in the collection, and then an inner loop that's shaking hands with each item in a collection. Oftentimes the same collection. That will give us O(n) squared. Now, what's an example of this? Selection sort or insertion sort, which is where you have a collection of items you want to put in any order, or you want to put in an order. So one of the sorts will basically go through the collection, find the smallest item, put it up front. Then go through the remaining collection, find the smallest item, put it second to the front. Repeat, third to the front. Repeat, fourth to the front. So you see we have to have two loops here, an outer loop and then an inner loop, which is constantly doing that movement. Another, the other sort will basically say, okay, let me compare these two. And if one is less than the other, I'll swap them. And I'll continue to do that throughout the collection. Then I'll start with the next position and swap. Continue to do that throughout the collection, then go to the next position and swap. And once again, in this case, we have a loop within a loop because we have to loop over the entire collection, and then within that, we have to continuously loop within the collection to move the smallest item to the front. So that gives us O(n) squared performance. And if you're newer to programming and I asked you to order a collection of items, that's likely a way you would think to do it. Would be to iterate over the collection with an outer loop and an inner loop and constantly be moving the next smallest item forward, or do the swap, 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 however you would do it. That's kind of like, oh yeah, that's how I would do that. But there actually is a more efficient way, which is something called a merge sort, which deserves a lecture all of its own, so I won't get deep into it now. But a merge sort effectively combines recursion with a loop. And remember, it was recursion that allowed us to flatten O to the n to O(n) log n when we were looking for Jones in the phone book. And that's when we're doing a lookup, is n to log n. That's easy because we're just finding one item. But when we're actually sorting something, that takes a lot more work because we have to do that finding an item, which is the smallest item, and then move it, and then iterate over the rest of the collection and find the next item and move it. So you see, sorting actually is way more work than just finding an individual item. But what a merge sort does in a really interesting way is it combines that outer loop with an inner recursion, and that gives us kind of a funny algorithm, which is n times log n. So we're taking that diagonal line, which is just the O to the n, the perfectly diagonal line, and we're multiplying it by the log n line, which if you remember kind of had that flattening curve, and it gives us a curve that looks like this. Now it looks like that's growing quickly, right? But what's interesting is let's compare it to the alternative. So remember, merge sort, O(n) log n, insertion sort, selection sort, O(n) squared. Now let's compare these two. So n squared is this curve right here, or on this diagram, this curve right here. O(n) log n is this curve right here. So if we look at the efficiency that we gain from a merge sort over selection or insertion sort, it's effectively the difference you see between this top beige line, which is an exponential curve, and this more brown line here, which is something between an exponential line and a flat line, but definitely a lot of savings from that. Now, the last big O we're going to consider is O(n) cubed, and this is one we'd want to avoid. This would be an outer loop of a collection that has an inner loop of a collection, and that inner loop has yet another inner loop. And once again, if you think mathematically, okay, outer loop is going to have to process O to the n times, right? The first inner loop is going to have to process O to the n times, but if we multiply that by the outer loop, which is also processing O to the n times, there we have our O(n) squared. But remember, we have a third inner loop, which is also going to process O to the n. So we multiply that O to the n times O n squared, and we quickly get O n cubed. So this is exponential, but to an exponent of 3. So this is one that we have to be careful of. I've seen this one, but rarely. Rarely have I seen the need to do that loop within a loop within a loop. There's another one that I don't have on this graph, but O n factorial, if you're familiar with like n exclamation. That's one that is really steep and really is not a scalable solution. I will say in my career, I've never seen a factorial operation, but that's why I left it off here. I don't have a really good example of it. But nonetheless, that's a look at big O notation, which I consider to be a very interesting topic. If you like math, you're going to like this topic. If you don't like math, I can assure you, if you spend a little bit of time studying this, you'll like math just a little bit more, or maybe you'll not dislike math as much, because this is a really interesting application of how we can use mathematics to make more efficient programs that run better and require less hardware. So as always, I hope this video was helpful, and I look forward to reading your comments. Thank you.